but we've been going over the structures of these three types of, I'm still getting F in chat. No, we saved it, we're good. Boy, thank goodness for Control Z, right? But we were going over the structures of these three classes of lipids, and again, my main concern with this is that people are able to distinguish between or among these and the other classes of lipids we covered last time, and then maybe 3 or 4 or 5 more that we'll cover yet today. From that, I will switch to the class notes, since I believe from here on, all of the structures are in the class notes. So that saves you the trouble from copying it down and me the trouble of writing them. Good, so now I've left that on the screen long enough. We see it's recording, that will make it onto YouTube. Phew, that was close. And actually, it's funny because after some certain point, I think it might be even after just chapter 6, I will have the material already recorded from last term. So I'll have to think about whether I still want to put up our classes in particular. I guess I might as well. But the thing is, should I forget, like I almost did here, then I have my lectures from last term, from when it was all online. Good, so let's now share the class notes. Yep, that's got the green borders, so those of you in chat should be able to see this. But let me just sort of, for my own good, kind of, at least for my own good, kind of read off what remains. We've got prostaglandins, we've got terpenes, steroids, and sex hormones, and that's basically it. And terpenes are kind of their own class of molecules, but the other ones that I just said, sex hormones, cholesterol, steroids like cortisone, these all kind of fall into the same structural class also. And I think you'll see that they have some structural characteristics in common. So prostaglandins you might have heard of. And again, I'm not going to say draw PGE1, but prostaglandins all look something like this. They really, to me, kind of look like a fatty acid, except that they have other functional groups hanging off, one of which is in general a 5-membered ring, kind of fused into the middle of this long fatty acid chain. I think you can see that this part of the molecule is essentially an unsaturated fatty acid. Interestingly, it's a trans double bond. So that's interesting, because remember with unsaturated fatty acids in general, we said that they will have cis double bonds. These are the molecules you find in your vegetable oil, in your olive oil, in your corn oil, things like that. So in a prostaglandin, that gets isomerized. Not all prostaglandins will necessarily have a ketone functional group, let's say, on the 5-membered ring, but I do notice that they generally have 5-membered rings, kind of in the middle of that chain. And prostaglandins are an important class of biomolecules. They're involved in the pain and inflammation responses, as you might be aware, and that's about the limit of my knowledge on that subject. Well, and like I said, I do not expect you to memorize particular prostaglandin molecules, but if you can tell a prostaglandin from a triglyceride, from a sex hormone, et cetera, that's going to be the main thing. And again, I think going forward in your upper level classes, that's the likeliest to do some good in terms of material that we can go over in this class. There are other molecules that are similar, except they don't have the 5-membered ring, so maybe this bond wouldn't be here. But these would look basically like fatty acids, except with other functional groups along the fatty acid chain, and that would include your leukotrienes and lipoxins. So I admit I don't know too much else besides these, other than that that like prostaglandins, they're involved in the pain and inflammation responses. So they look also very similar, but I think what makes prostaglandins like leukotrienes and lipoxins is you see other functional groups, like this ketone, like these alcohols, along the fatty acid chain. My understanding, at least, is that's what makes them similar. What makes them different is that prostaglandins have this 5-membered ring fused in the middle of the chain, whereas leukotrienes and lipoxins don't. You could maybe imagine what this would look like with this bond broken and replaced with bonds to hydrogen. Then you would probably have something similar to a leukotriene or a lipoxin. So that's at least my understanding. So, and again, those are another important class of biomolecules, and I think you'll agree. I mean, yes, there's a carboxylic acid group. We got a couple alcohol functional groups. Those are slightly water soluble, but overwhelmingly, I think if you were to describe this molecule and be fair in doing so, you would agree that it's overwhelmingly described as being lipophilic or hydrophobic. Look at all of these hydrocarbon chains. So we would certainly expect something like this to dissolve in water with great difficulty and only at very small amounts, and to be much more soluble in fats. Good, so much for those. Oh, that was scary. I thought that there was this big space here and all my molecules that disappeared. So no, but terpenes, I think, are another class of molecules we need to mention that belong in the category of lipids because they're, again, almost completely hydrocarbon-containing molecules. And these things occur in nature quite a bit. You find a lot of these things in plants especially. You'll find them in flowers and skins of fruits and tree bark and all that good stuff. So terpenes show up a lot. I would say the general name is terpene. Sometimes you also see the word terpenoid. To me, that's kind of a distinction without a difference, those two terms. But the simplest type of terpene, what you would call a monoterpene, it has 10 carbons made up of 2 5-carbon units. And the 5-carbon units that make up terpenes, and not just monoterpenes, but also larger terpenes. The 5-carbon unit is a molecule called isoprene, which is over here. Isoprene, we could call that 2-methyl-1,3-butadiene. How does that sound? But everyone just calls it isoprene. And I think you can see in molecules like these two, these are typical monoterpenes. And the way we know they're monoterpenes is because they have 10 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if I look at that, it's not a fatty acid, it's not a triglyceride, it's not a prostaglandin, it's not a phospholipid, it's none of these other things we've been talking about. So those will tend to be terpenes. And myrcene does indeed occur in plants, I think in certain flowers. Citral will be another. So these can have other functional groups. We have an aldehyde functional group over here. But something peculiar that I think you'll notice about terpenes in general is they'll always have these sticky outy bits. And those come from the methyl group in isoprene. So you can pretty clearly see, here's a 5-carbon isoprene unit, here's another one over here, because it's got this sticky outy bit over here. Or in myrcene 1, 2, 3, 4, 5, here's an isoprene unit, and here's the other isoprene unit. Boy, if you broke this bond, you would have isoprene. So they're usually pretty easy to pick out. Menthol is another naturally occurring molecule that falls into the class called terpenes in general. And I think this too is a monoterpene. So there should be 10 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep. So what you need to know about terpenes is how to recognize them in comparison to other lipids, how to tell them apart. And I just told you how to do that. They're going to consist of 5-carbon isoprene units. And monoterpenes will have 2 such 5-carbon units. So monoterpenes will have 10 carbons. And there are a couple larger terpenes that we'll get to in just a moment. But that's how you know. You can tell by there not being any of the other types of lipids, and especially by their being made of 5-carbon isoprene units. So let's see, 1, 2, 3, 4, 5. Maybe this is one isoprene unit over here, and here's another one over here. Notice this little sticky outy bit over here, this methyl group. That will come from that pendant methyl group in isoprene. So you need to know monoterpenes have 10 carbons. Monoterpenes have 10 carbons. You can keep going. The prefix sesqui means 1.5. So you don't run into it much, but that's what sesqui means, 1.5. And so a typical sesquiterpene will have 15 carbons, and you can know that just by counting them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Indeed, it is 15 carbons. And other than that, if you look at that, it's not a fatty acid, it's not a triglyceride, it's certainly not a steroid or sex hormone, which we'll get to those pretty soon. And not only that, you can see the 3 different sticky outy bits over here that come from that methyl group on the isoprene. So I think you'll get a chance to practice that in OWL, but picking out 5-carbon isoprene, please tell me vitamin C is a typical citrus. I'm not sure that vitamin C is a water-soluble vitamin. So I don't think it falls into the class of lipids. I should know the structure. I'll look it up in just a moment. I know it's a 5-membered ring with crap loads of oxygens on it. Yeah, so anyways, so here's one 5-carbon terpene unit, 1, 2, 3, 4, 5, here's another, and then there's another 5-carbon terpene unit on the end. Now, vitamin A would be an example of a fat-soluble vitamin. You know, you've got water-soluble and fat-soluble vitamins. So I should know this off the top of my head, but your water-soluble vitamins are what? Vitamin C, certainly. The B vitamins are water-soluble. I feel like there's one more that might be water-soluble. I know vitamin A is fat-soluble. And again, not surprising. Just look at that structure. The only polar group on it is this OH group. And other than that, you got 20 carbons. Vitamin K is water-soluble. I wouldn't be surprised. And if you looked at the structure of vitamin K, I bet you would not. I certainly don't expect you to memorize it. I don't have it memorized. Well, we'll look them both up in just a moment. It's not like we don't have time. But vitamin A would be, in general, a terpene. More in particular, we would call it a diterpene, because it contains twice 2 is 4 5-carbon isoprene units. So vitamin A should have 20 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Yep. So that's how you recognize it. That, and you look at it and you say, that's not a prostaglandin, that's not a triglyceride, it's not any of the other classes of lipid-soluble molecules that we'll need to know. But they all have a certain number of 5-carbon units, 5-carbon isoprene units. I do not know what the prefix according to corresponding to sesqui is. That means 2.5, though there must be one. I'm sure there's 2.5 terpenes, whatever they may be called, that will have 25 carbons. And yes, indeed, there are triterpenes that will have 30 carbons. They all fall under the general umbrella of terpenes, but you can tell whether it's a monoterpene or sesquiterpene or diterpene by how many carbons are in it. So a monoterpene, again, has 2 5-carbon isoprene units for a total of 10. A sesquiterpene will have 3 for a total of 15 carbons, and a diterpene will have 4 for a total of 20 carbons. And that's, I mean, frankly, that's all I know about terpenes. I would be happy if you knew that much. Let's, though, look up vitamin C and vitamin K. And I know that when you see the structure of vitamin C, you will not be a bit surprised that it is a water-soluble vitamin. It's got polar groups everywhere. And so molecules like that are not mentioned in this chapter. They are not lipids, right? They're water-soluble. Vitamin C. Come on, structure, come on. Oh, you guys are lame. Google. Well, I guess you could blame it on operator error, vitamin C structure. There we go, that might work better. A, D, E, and K are fat soluble, okay. So not, but look, here's vitamin C. Look at all these alcohol groups. You got a cyclic ester. Here's more OHs. It looks more than anything like a sugar, doesn't it? To me, that reminds me very much of the structure of ribose that we were discussing just a few lectures ago. Oh, you can see it. I know why you can't see it. Now you can see it. So there's the structure of vitamin C. No, you do not have to memorize that. You see, I didn't have it memorized. But now the proportion of hydrocarbon to polar oxygen-containing groups, now I think this molecule, you'll agree, is characterized much more by having water-soluble oxygen-containing groups. These can interact with water molecules by hydrogen bonding. And so you still can't see it? I thought I chose, yeah. Oh, now you can, okay. But yeah, so that's, so you're saying A, D, E, and K are the fat-soluble ones. So what does that leave? The B vitamins, I don't think there is a vitamin F or G. So maybe it's just the B vitamins. Let's do vitamin B6. Just as an example. There you go. So that's vitamin B6. Look at all of these OHs again. Look at this pyridine type nitrogen. Actually, I don't think, we're not really able to see the whole structure unless here we go. There's your vitamin B6. Okay, I guess it is a methyl group. So that's one of the, well, let's see, that's vitamin B6. This one is a different B vitamin, but they're not really saying which. And here's yet another one. And again, alcohol functional groups, amine functional groups, plus the pyridine nitrogen, these are all going to be able to undergo hydrogen bonding with water molecules. And so a much higher amount of water-soluble functional groups and water-soluble vitamins than you will find in fat-soluble vitamins. So that's why these guys, the B vitamins and vitamin C aren't mentioned in this chapter, because those are not fat-soluble, those are water-soluble. So they are not part of the chapter. They are not part of the class material. Good, but I think that's basically it for that. Let's go back to our class notes. And last but not least, all of these molecules that, let me do this, close window. All of these molecules that are built on the 3 rooms in a garage framework. Let me switch to my whiteboard for just a second so I can show you what I mean. So all of these molecules have a 4-ring or tetracyclic framework in common. They always involve 2 6-membered rings fused like this, then another 6-membered ring up here, whoops, and a 5-membered ring over here. So they always have that 4-ring structure in common. And biologists and biochemists, when they want to refer to these individual rings, they call this first 6-membered ring the A ring, and then the B ring, C ring, and the 5-membered ring is the D ring, as you would have guessed. And they'll talk about such and such a group being on the A ring or on the B ring. But all of those other classes of compounds that we said, all of the sex hormones, the steroids, cholesterol, and also bile salts, those 4 types of compounds all have this tetracyclic ring system in common. And like I said, I sure don't expect you to memorize particular ones. Though I would say, I don't know that you need to memorize it, but it would probably do you some good to be able to pick cholesterol out of a lineup. I always look for the OH group over here, and the alkene over here, and then this funny alkyl group with the whale tail here at the end. That's always what I look for in order to make me think that it's cholesterol. But I certainly wouldn't expect you to memorize it. I don't have it memorized either. But that's a nice one to be able to recognize, I would say. Over here, you've got cortisone, and that's a steroid hormone. And again, I would not expect you to draw cortisone, but I would expect you to look at this and say, well, this is not cholesterol. It's also not a bile salt or bile acid. So it must be some other, either a sex hormone or a steroid hormone. And here's progesterone. That's an example of a sex hormone also. I even have estradiol and testosterone. Estradiol is an interesting one. Look, the A ring is aromatic. So that's allowed. It will still be a 6-membered ring, of course. But the other ones, that ring is not aromatic. So other than that, I think you'll agree, all of these molecules are pretty similar, and even more similar than different to cholesterol. The odd one out in this class that still has the 3 rings in the garage, still has the A, B, C, and D rings, is bile salts, or they're also called bile acids. And I mention these because I think these are going to come up in upper level classes for you guys. The thing to be aware of with bile salts is the ring fusion between the A and B rings. you can see that these are fused in such a way that the methyl and hydrogen here, whatever these two groups happen to be, are cis to one another. And I have this in the class notes too, but that's a hallmark of bile acids or bile salts. And again, I would never expect you to memorize a particular bile acid structure, but it's that cis ring fusion that has these two groups being cis to each other that makes it a bile salt. If you look between the A and B rings and instead either those two groups are trans, or there is no cis-trans distinction owing to one or both of those two carbons being sp2 hybridized, then it is not a bile salt, it's something else. It's cholesterol, it's a sex hormone, it's a steroid. And I think you can see that's the case. Over here on cholesterol, this carbon is sp2 hybridized, so game over, there is no cis-trans distinction in that ring fusion. Same thing over here in cortisone, that's sp2, progesterone, sp2, testosterone, sp2. In estradiol, they're both sp2, game over. So that's how you know that these guys are not bile salts, because that ring fusion is not cis. Same thing with cholesterol. That ring fusion is not cis. But in a bile salt, that ring fusion will be cis, always. And as far as I'm aware, there's no exceptions to that. So let me see if there's anything else. I mean, I think that's basically it. And again, my main goal for you guys, and what I think will do you the most good going forward, is if you can, first of all, recognize a lipid as opposed to something else like a water-soluble vitamin. Even if you don't, I wouldn't expect you to memorize vitamin C, but if you looked at that structure, I would expect you to be able to say, that is not a lipid. There's way too many OHs on that. I think that will do you good later on. And then also to know a triglyceride when you see it, even to know a prostaglandin or a phosphatidate when you see it. I think that will only help you later on, because insofar as you find those things mentioned in your upper level classes, they are not going to go over the structures like this, like we're doing here. And I really think that even at this level, having had half of one semester of an organic chemistry class, yeah, these molecules are big by and large, but we can understand their structures based on what we've gone over already. At least that's my opinion. So that's been my experience also, going back some years. So, but check out the class notes. I've put all that there in the class notes. And yeah, I think that's basically it for chapter 15. So I was going to spend a little bit of time on the reef session. Let's change gears for a moment and we can practice drawing a dinucleotide. And then if we have 5-10 minutes left for me to work other problems for you guys, I'd be happy to do that. Questions on lipids before we go there, though? Heck no, right? It's done the exam, so out of sight, out of mind. Trust me, I get it. Good, well, let me close the class notes. And as I said, this is just 10 points for attendance, so please register your attendance. Even 13 messages, good heavens. I'm gonna dress up as testosterone for, let's see. Oh, that's good, ho, 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 is vitamin C Santa. Which one is the bile salt is the one with the cis ring fusion. Do we have to Zoom while taking the test, or is it just if we have questions? No, you do have to Zoom. We'll do everything like last time. And I have the, such a dumb, oh no, I've heard worse. Okay, so I'm going to leave this up. And yes, you can see the answers, but it doesn't matter because it's just 10 out of 10 for attendance. Normally I will, at least I think I left the answer on there. Yes. So here I've given you the structure of cytosine and the structure of ribose. So put together two cytosine-containing nucleotides and make it of the type that you would find in RNA. And then as a last instruction, put a diphosphate at the 5' end, the free 5' OH. Make it, instead of OH, O diphosphate. And so these are those structures. I would never expect you to memorize those. I certainly don't have cytosine memorized. Ribose, I guess I do. That's not so hard to memorize. but maybe take a couple minutes to think about that. Then I'll call you back and we'll go over it. And then any other time left will be, if you want me to do some aromatic reactions, if you want me to do some reactions with amines, no worries, just let me know. Just don't want to lose track of time. This, by the way, is exam material, although again, I can't ask you a question like this since it's multiple choice. So this really is going above and beyond. Which is good. It's better to be able to answer questions that are too hard or of a different format than not being able to answer questions that are hard enough. If we're going to err in one direction or the other, let's err in the first direction. But I will just say we had some questions in chat, which I'm sorry I missed. We had some questions on bile salts. You'll be able to get that from the YouTube video because I talked about that, and we are recording now. Well, that clock just went to 3:35, so here's how I drew it. So if I'm doing this right, wait a minute. Can you guys in chat see that? Let me double check. Yeah, we have that selected, so you should be able to see that. So then for oh, this is annoying. So I can see the pointer here, but not on the screen. So, well, anyway, let's see. I guess we'll have to do it once for the people in chat and once for everyone else. So these are our two cytosines. I've connected them from nitrogen 1, as they call it. This is the one with the NH. So we'll take away the hydrogen and form bonds to carbon instead. And I'm saying, for those of you in person, here's our two cytosines. And again, I sure don't expect you to memorize the nitrogen base structures, but notice how they're connected to the 5-membered sugar rings via that NO-acetal that we talked about the other day, meaning that you have a carbon that's between a nitrogen and an oxygen, both sp3 hybridized. Why are there two phosphates at 5' carbon? Because it said draw a diphosphate group at the 5' end. So that's following that part of the directions. It said put a diphosphate group at the 5' end. Now, between this 3' and that 5', between any two sugars in any nucleic acid, whether RNA or DNA, there's always exactly one phosphate. Always, always, always. No exceptions. That part's invariant. But the question said to put a diphosphate group at the 5' end. If it had said to put it at the 3' end, we'd have put it down here. So other than that, it said to make it RNA type, so we have OH groups pointing down on the 2' carbons. If this were DNA type instead, these would both just be CH2s, and we would deoxygenate it. Again, that's the D in DNA. We deoxygenated the 2' carbons. So since we see OHs there, that tells us we're looking at an RNA type of dinucleotide. And like I said, I believe that this level of understanding the structure, first of all, will be of some help for maybe not all of you, but for a lot of you going forward. And also, I think that's something we can understand at this level. It's amazing how we can do half a semester of organic chemistry, and there's really nothing here that's out of reach for us, I think. Yes, it's kind of a big, scary molecule, but when you break it down into its component parts, I think it's manageable. So that's going to wind up on eCampus eventually. That's at least how I chose to draw that time. Let me get out of there and go back to the whiteboard. But I think that's all we will need for, okay, so we're at 3:38, I've got 7 minutes. Let's see, so should I do something with aromatic compounds? Should I do something with amines? You've probably seen enough of nucleic acids at this point. Amines, okay. So what are some things that you'll have to know about amines? Well, the study guide does say that nomenclature of amines, within reason, you know, is certainly reasonable. I would expect you to be able to draw something like butylethylamine. I think that would be completely fair. So what would that mean? Well, it would mean that on our nitrogen, we've got a butyl group and we've got an ethyl group. 1, 2, 3, 4, there's our butyl group. 1, 2, there's our ethyl group. And we also still have 1 hydrogen attached, because it mentions only those 2 alkyl groups. That would be a very fair question. Which of the following is butylethylamine? Maybe. Now you know I'm not going to put that particular one on, but a question like that would have been completely fair. And I hope you can also recognize this as being a secondary amine, right? Because you have 1 H still attached directly to the nitrogen. Tertiary amines of only 3 alkyl groups. Primary amines of just 1 alkyl group and 2 hydrogens. And of course, if it's 3 hydrogens, NH3 is ammonia. Ammonia is not organic. I'll forget you ever went through this. What about reactions? Well, we did some I was going to go there next. We did some reactions of amines. We said that if you treated an amine with any strong acid, like let's say we treated this with HCl, well, then you would get the conjugate acid. So we have our ethyl group and we have our butyl group still. 1, 2, 3, 4. Plus charge in the nitrogen, and if you need to show the counterion, it would be chloride. So what other reactions did we do? We said that you can take an amine or ammonia in excess and treat it with an alkyl halide, like what about, oh, I don't know, benzyl bromide. That's a favorite one. And remember, benzyl bromide is benzene ring CH2Br. Benzyl bromide is a different critter from bromobenzene. And so at first, you will get a quaternary ammonium species, CH2, and then the benzene ring over here. I'm hopeless at drawing benzene rings on their side. I don't know why. I've just never been good at it. And then you still have the ethyl group and still the butyl group, plus charge on this. And then remember, you need to treat this with a base to neutralize it, to get rid of the proton. Maybe sodium hydroxide or potassium hydroxide would also certainly work. And so OH minus is going to take off H plus, and you'll get a water molecule, and you'll get your tertiary amine. So these are some of the reactions we went over. And now you've got your free amine back with the lone pair on nitrogen. So you can convert a secondary amine to a tertiary amine, primary to secondary, or ammonia to a primary amine using this type of method. We did several examples of that in class, and I know it's on your OWL assignment also. And I'm probably forgetting some reactions also. I guess we did acylation also, where you treat an amine with an acid chloride or acyl chloride, and you get an amide out at the end. We did examples of that reaction also. All this is in the study guide too. I'm not keeping any of this hidden anywhere. It's not meant to be a trick. Good, so those are some of the reactions of amines. What did we do with aromatic compounds, since I have 2 minutes left? Well, we did to some degree about the nomenclature of aromatic compounds. I think there are several of those monosubstituted benzenes that they just show up so much, it's worth knowing their names. Things like benzoic acid, benzaldehyde, toluene, aniline. These molecules are so common and mentioned and used everywhere. Phenol for hydroxybenzene. And you know, I get asked a lot, is it always phenol no matter what, or is it ever named as a hydroxybenzene? Is it always toluene no matter what, or is it ever named as methylbenzene? I'm sure you can find examples where they're named some other way, but in my experience, we try to use those common names. Diethylmethylamine is named correctly. Sure, that would be a thing. And I like how you put the methyl second, because E comes before M. And it looks something like that. Absolutely, that's a thing. But back to aromatic compounds, we did just a few of the electrophilic aromatic substitutions, right? We said that if you treated benzene with, just to pick one example, bromine and either aluminum bromide or iron 3 bromide, you would expect to get bromobenzene. It will substitute one of the hydrogens for bromine. And there were 2 or 3 other similar reactions. The inorganic side product would be HBr. So that's one of the reactions we discussed. You were not responsible for directing effects. I certainly don't expect you to learn about that. But that being said, to a point, you guys can still handle them. For example, if I told you that we're going to treat, benzaldehyde, let's say, with some mystery reagent, and in the end, we will get you could call it 3-methylbenzaldehyde, you could call it meta-methylbenzaldehyde, you could call it meta-tolualdehyde. Any of those names would be fine. I think they're all equally good. Well, we don't know anything about why the aldehyde group makes the new group go here. I mean, I do. You don't, but you don't have to know. All you have to know is the only way these two structures differ is that we've added a methyl group, and so I think we know how to do that. We'll take some methyl halide. In real life, we'd actually use methyl iodide, by the way, as opposed to chloromethane. Only reason being that chloromethane is a gas at room temperature and methyl iodide is a liquid at room temperature, and so is much easier to use. That's kind of inside baseball, but if you put CH3Cl, I would accept it. But again, remember, you're not going to have to put anything. It's multiple choice. You'll be shown all the answers. And you also need either aluminum chloride or iron 3 chloride or something like that as a catalyst. So something like that would be the answer that I would look for. Should be there in one of the choices if it's asking you which is the reagent that you'd use. And again, you don't know that the aldehyde functional group is meta-directing, that it makes the new methyl group go in meta. I know that, but you don't need to know that in order to be able to answer the question. You don't need to know about directing groups in order to say, well, this is the new group that got added, so my reagents must have been something like this. If that makes sense. Oh, and I'm out of time, like by 2 minutes. Sorry about that. I never cease to amaze myself.